Okay, I'm going to an elementary theorem. It's quite important in its own way, but I'm doing it more to show you how proofs work than because the result's important. Uh, we've got various results for all x. Just zoom in a bit. For all x, we know that ex equals x and xe equals x. So what we say here is that E is a left a left neutral and a right neutral element, a left identity and a right identity. And also for all x, we know that x dash equals x dash x equals your identity. So to multiply by x dash, you can do it on the right or the left, and you get back to the identity. What I'm going to do now is to ask if E is a left identity and if x minus 1 is a left inverse, do we have a group? In other words, if we've got a left identity and a left inverse, are these things also right inverses as well? I'm also going to assume associativity, and we'll see why very shortly. Okay, so let's just write down what we know so far. What we know is that ex equals x for all x, and we also know that x dash x equals e for all x. Well, so it's the left inverse. If I ask, what's the inverse of x dash? Well, I'm going to write that x dash dash, and that equals e as well. So I'm using the existence of a left inverse for x dash, and I'm calling it x. I could call it anything I like, but I'm just going to call it x dash dash, just because it makes it easier to remember. And of course the inverse of the inverse is the element you started with, but we don't know that yet, because we don't know that we've got a group. Okay, so what I'm going to ask is, what is x dash equals what? Of course, I want it to be the identity element, but I don't know that's the case yet. Okay, well we know that E is a left identity, so x dash equals E x dash. Okay. And now I'm going to use this expression for E. I'm sort of using the group axioms against themselves. So that's equal to x, just rewriting E, x dash times x dash equals, and now because it's associative I can write x dash dash x dash x dash. I'm just re-bracketing that. And we know from this line here that x dash x is equal to the identity, because x dash is a left inverse, equals x dash dash identity x dash equals x dash dash x dash, which equals the identity, because x dash dash is by definition a left inverse of x dash. So summarising all this lot, x dash equals all these things, blah 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 blah, equals the identity. So therefore x dash is a right inverse of x, because we know that x dash equals the identity. Okay? So what else do we need to prove? We need to prove that E is a... Which way around have we got? We know that E is a left identity. We need to prove that E is a right identity. So I ask, what is xe equal? That equals what? Well, it better equal x. Okay, well let's just expand E with some of the other expansions that we know. Well, xe equals x times x dash x, because we know that x dash is a left inverse, which equals x dash x, and from this result here we know that's equal to ex, which is equal to x. So what we've established is that first of all x dash is a right inverse of x, and secondly that E is a right neutral. Sorry, E is a right identity. So in other words, E is a left identity and x minus 1 a left inverse together imply with associativity that E is a right identity and x minus 1 is a right inverse, and therefore if the operation is closed and associative then we have a group. So my original axioms were a bit redundant because we don't need to assume E is a left and a right neutral element, and the inverse is a left and a right inverse element. We only need to assume that they're left neutral and left inverse respectively. I'm showing you this because I'm showing you how we can use associativity over and over again. We needed to use associativity in all these different steps here, or many times in these steps here, to establish our result. But I want to show you the kind of thinking that you need to do in group theory in order to prove theorems. And I'm going to stop there.